morning. How's everyone doing? Did you have a good time last night with some drinks and food? Hopefully you got out to see a little bit of Portland if you had some time last night. My name's Kevin Schneider. I'm a Chief Product Strategist at Autodesk. Fortunate to be part of the Fusion team for almost 10 years. In July, we celebrated our 6th-year commercial release, so super excited to be here. Portland's home for me, so it's super exciting for me to be able to invite you here to the first academy in the United States. Portland is essentially the home of Fusion. It started here. It's developed all over the world now. So it's a huge team trying to build the best product we can for you, but spiritually there's a lot of people in the room here who were at the very start. So for me, being from Portland, it's the best opportunity for me to share with you the story of Fusion and to bring you all together into one room so that you can share your stories with each other. And that's what the Academy is all about. So if you just look around the room and you look at some of the faces here, this is literally the best group of Fusion users in the world in one place. So it's the best place I could ever be. I couldn't imagine being anywhere more exciting than in the room with you. A little bit about the Academy. About 4 years ago, Yuji, you saw his face at the end? He single-handedly started the Academy in Tokyo. Now, I don't really want to do numbers too much, but you should know that the Tokyo Academy that he started was a week and a half ago. Say hi to Tokyo, everyone. Their event was bigger than the US event, so we've got a lot of work to do for next year to beat the Japan team. And just to make that real, give me a minute, I want to take a picture of the crowd so that everyone here can say hi to Tokyo next year. So everyone on count of 3. 1, 2, 3. All right. Challenge accepted. It was an amazing event. You'll notice in the front row, there's a 11-year-old boy there. He did a 360-degree vision system for a robot that he designed in Eagle and Fusion using a parabolic mirror in order to do 360-degree vision. He did a complete presentation, including the mathematical formula, how he did the vision recognition system, and the robot designed in Fusion by himself in front of a room of 450 people. It was totally inspiring to be able to see his presentation. And that's really what Academy is all about. It's a chance for you to be amongst like-minded individuals, for you to learn from experts, and for you as an expert in your field to share that knowledge with others. So if there's one thing I would ask you to do at the Academy is talk to your fellow Fusion users, share your experiences and stories. Because everybody has something to learn from someone else, and everybody has something to teach someone else. Because Fusion is a pretty big product, so there's quite a lot in it. We always have opportunities to grow, and who better to grow and learn from than fellow users like this. So I'm going to spend a little bit of time talking about Fusion and how we got started. About 10 years ago, we started to see some problems with how data, experience, and the tools you had to use work together. And after a while, we realized we should and could do better. We should be able to deliver an end-to-end product development platform that gives you answers to how you manage and transport data through your process, an experience that makes that coherent through every stage of the process, and makes it much easier to get access to technology that was locked up into multiple vendors, multiple applications, multiple licensing systems, multiple training systems that just was too hard to make work together. And out of that vision, out of that mission, Fusion was born. So today, Fusion's got tools. Whether you want to do conceptual design, being able to move surfaces around dynamically, it has collaboration tools so that you can connect with each other, manage tasks, tell each other work that needs to be done. It has detailed design tools so that you can take those concepts and generate engineering data on top of it. And to take that engineering data, generating drawings or running simulations so that you can validate the performance and the weight, strength of the parts that you're working with, evaluate different sizes, materials, all of that in a single workflow. And finally, it has tools that you can use to manufacture those parts, taking them out directly to your shop floor to manufacture, machine, injection mold, run additive machines, whatever you may require. So that end-to-end experience is really trying to fundamentally change those three pillars that we saw all of you struggling with. Now, last year, we introduced something that we'd been working on for a long time. It's called Generative Design. So Fusion 360 with Generative Design now gives you a completely new tool set to tackle that problem. When CAD started, at best, it could help you document an idea that was already in your head. But now design has changed. Those challenges we saw before are obstacles in your way to getting better products built. But even more interestingly is the way you build products, the amount of information that was locked up in manufacturing, the amount of information that was locked up in engineering, never really could inform each other to make better decisions. This convergence of designing and manufacturing, if we can bring those together to you and provide some automation to make that faster and easier, we believe we can give you something truly unique, and that is what generative design is for. Will is a Japanese customer. They designed the personal mobility device. It's meant to help people get around, but it also needs to pack up and fit in the trunk of a car. So it has strength, weight, and safety factors that need to be met. On the front of the wheel is this bracket. It's a part like many you may make, and there's many parts like it. And you might design this part with sketching, extrudes, and fillets. I think we could all probably sit here and figure out how we might make that part. Generative design gives us an opportunity to change the way we think about how we design. In this case, we're not going to model the part. We're going to model the problem the part needs to answer. So green areas are areas where we know we need attachment points. Red areas are areas where we know we need clearance. Next, we can define the performance. We know particular loads that need to be met, and we know materials we might make it out of. And more interestingly, now we can start to define manufacturing processes we might consider to make it, whether it's additive, machined, die casting, plasma cut from plate. This gives us the opportunity to describe the problem, not the answer. So why is that important? First of all, we're going to get back valid solutions to the problem we've set up, but we're going to get more than one. We might get a multi-axis, an additive, what we call unrestricted, which is just give me the optimized shape. We also have some new forms for 2.5 axis, 2-axis, and die casting as manufacturing processes. So the first thing that we get from generative design that we wouldn't have had before is valid answers for each of these manufacturing processes. And that gives us an opportunity to explore a broader swath of the problem and potential solutions to that problem. And that means we can pick the best answer for our particular problem or design constraints. Now, we need to make sure it performs. So inherent to generative design is validating factor of safety. And here we can see each of these parts meets our minimum factor of safety. It also means that we can validate the weight, and we can see the weight savings from each of these three options. And that gives us an opportunity to choose a compromise that's best for our problem. Now, looking at those parts, one of the things I'm sure the machinists in the room are thinking about, some of those parts are pretty darn expensive to make, and you're absolutely right. And that's why with 2.5 axis now in Fusion 360 generative design, you have access to a very practical and very cost-effective method for manufacturing that you haven't had before. This should fundamentally open up generative design for many of you who may have looked at those parts in the past and said, I can't make that, that's too expensive, that's not practical, I don't have an additive machine. I think you all can see the 2.5 axis is one that may be really interesting for you and your business to look at. And as I mentioned, you don't get one answer. You get literally hundreds of answers back if that's how many options you give it. This gives you the choice of what is the right answer for your problem and lets you explore that broad problem space. The time it takes us to generate this many options, we could probably manually model 1 or 2 parts. Just think about the opportunity that that represents for you in how you may be designing your own parts. 2 parts or hundreds of literally valid, ready-to-go parts based on many different materials and manufacturing options. Super powerful, and I really encourage you to attend some of the classes if this intrigues you. I think it should. Now, the machining time, we recognize that costs money. So one thing we're super excited to talk about here is the addition of costing information. This is powered by a company called A Priori. These are experts in DFMA and costing, and they're providing ranges of cost per option. And I encourage you Wednesday afternoon to attend Daniel's talk about the roadmap, because he's going to show you a lot more. But with that costing information, now as a designer, look at this range of options. We can look at safety and cost with cost range. Never before have you had access to this much information in designing products. And this is just the tip of the iceberg for generative. We're only getting started on the power we're hoping to deliver. Now, you have to make those parts, and some of those parts are complicated, and you need more automation and tools to make them efficiently. So just a few months back, we announced our first extension. It's the manufacturing extension, and it includes automation that comes from best-in-class tools like Delcam and NetFab. So if you haven't looked at the extension, let's go back to the wheel. You get access to automation. Maybe you used a parallel and a scallop, and you finagled the angles between the two to machine complex 3D surfaces. Steep and Shallow does all of that for you and increases the quality in the overlap between steep areas and shallow areas on that form. Drilling automation creates tools and identifies holes across the entire part, providing automation to speed up drilling in your parts. Surface inspection provides you access tools to validate the shape, and in process, use that information to improve your machining quality. And lastly, if you're doing any additive manufacturing, you get automation for supports, orientation, and sending data directly to additive machines for manufacturing. So just the start of the extension for some very powerful automation, and it will help you bring all of the current parts you're designing and hopefully the exciting parts in generative design that you're working on to life. Now, to get access to the manufacturing extension, we've done something different. In the past, you might have had to spend $10,000 or more on a specialty application to do that kind of automation. With a manufacturing extension right inside of Fusion, you can pay on demand for access only when you need it. So whereas in the past, you may have had to cobble together lots of applications to get specialty tools, in Fusion, it's our mission to give you access to those tools very easy and cost-effectively and on demand. So you buy Fusion for your yearly subscription. If you're doing generative, you only pay when you do that study or use the outcome that works for you. If you want to offload rendering or simulation, you can do that per job. And now with the extension, you can buy automation only when you need it at a cost you've never seen before. And the value on these areas is only going to increase over time. If you've got questions about the extension, ask any of us. We're happy to tell you more about it. But I think this is going to be super exciting in the way that we can bring new functionality to you in ways that you've never seen before and provide access to powerful automation that you've never had before. So, just to recap a little bit, end-to-end product development includes our data management, our design, concepting, engineering, simulating, and manufacturing. All the capabilities we need to build a product, and it's growing every year. At this academy, I want to just kind of give you a teaser. Every one of those boxes I showed, there's somebody in this room who's teaching a class on that particular topic. So if you want to learn more about surfacing, hit Jake's class. If you haven't done any machining yet, hit up Kevin's class. Every one of those areas has an expert, whether it's ECAD or MCAD or concepting, simulation. If you look around this room at everyone else, there's somebody who can share a story with you, share expertise on that particular area. And that's what makes this event so incredibly special. I mentioned Portland's home for me. It's really, really exciting to be able to have so many of you here. There's folks in this room, some of you I've known for 15 years or longer. Some I'm just meeting for the first time. But I really want to just heartfelt say thank you for coming. It's a super exciting event for us. Mostly that we can get all of you in the room together to share your experiences and these classes. So that makes this really special for me because I've learned a lot from you and others. And one person I've learned probably the most from over the years is a gentleman by the name of Carl Bass. You may know him. He was our previous CEO, but he's a consummate maker, incredibly friendly in sharing his stories. And he's going to come up and share a little bit with you what he's been doing with Fusion and in general in his making. So with that, let me welcome up Carl. Knock it off.
Good morning, everybody. Actually, I have learned the most about CAD from my very first lesson, came from Kevin, and to this day, whenever I have a question, I know where I send my email and text. By the way, for the rest of you, kevin.schneider@autodesk.com. He's happy to answer all of your questions. So, what I wanted to do this morning was just talk about making and tell you about some of the projects. It's really great to see everybody. I've been gone from Autodesk for 2 years, and I wanted to tell you a little bit about some of the things I've been doing. I've been working in my shops a lot and building all kinds of things. I've been working with a number of interesting companies, been traveling around the world, and having all kinds of fun. So I was going to share some of those stories and experiences this morning. But the main point was talking about how do we create things and how do we solve problems. The essence of everything I've worked on is about problem solving. And I've been really interested in how do we go about formulating those ideas, how do we bring them to fruition, and how do we bring them out into the world. But first, let me tell you about some of the things I've been doing lately. So I just got back from a trip to Africa. So one of my sons, my older son, had graduated from graduate school, and he wanted to go on a trip, and we had a couple weeks, and him and my wife were convinced that we had to go to Africa. We had to go on safari. They kept on saying it was on their bucket list, and I started reading about it. It's halfway around the world, and you need 42,000 shots, and they kept saying bucket list, and I kept saying it's on my fucket list. I really have no need to go to Africa. Turned out I was completely, absolutely wrong. It was the most incredible experience. I had a great time, was there for 2 weeks on safari, got to see animals like this up close. And the one thing I thought about as I did it was the thing that's so striking, because Africa, particularly in the hinterlands, is so primitive, is of all the inventions and discoveries that allowed us to get out of Africa. I mean, when you're there and you're roaming around with animals that are bigger and stronger and faster, and you're that far away from the lion having an impala breakfast, you start thinking to yourself, how the hell did we manage to do this? And you think about the invention of fire and steel and everything that came between where we were and how we got to all the things we'll be talking about for the next 2 days. And so it's with that backdrop that I want to talk about making and how I got interested. Now, many of you grew up in a garage. I didn't grow up in a garage. I instead grew up not really making that much. What I really did was I had Lincoln logs, I had blocks, and I had erector sets. And that was, and for those of us old enough in the audience, those are the Legos of our generation, were the erector sets. And so I built things out of that. But that was just play. But there was this one moment at which I realized that I could have an idea and turn it into a thing. And I think that's a magical moment for everybody, where you realize how things are designed, how things are made. These are just choices. They're like chocolate and vanilla. I can use a screw, I can use a bolt, it can be black, it can be white. And for me, that moment was this. So this is me, and what we did is we decided we wanted to go down this river, and so we bought Army pontoons. These are inflatable pontoons that were used for bridges in World War II, for Jeeps to go across. We blew them up, and we tied a couple 2x4s to them, and we floated down a river in southern Oregon called the Illinois River, which is a tributary of the Rogue. And by the way, while I look very happy there, about a minute later, I fall off this thing, and I swim the entire rest of the rapid. I come up, and this old-looking prospector comes up to me with a stick, and he goes, "Son, you just about bought the farm there." And it was true. I had swam the entire rapid, but it's nice that I have a picture of the fun part of this. But for me, this was the moment in which I realized that I really could just have an idea of something and do it. And in the 40 years since then, I've been watching people go through that aha moment. I've watched my kids do it. I've watched thousands of people go through that experience of just realizing they have the power, they have the capacity, we all do, to make anything that we want to make. So now let me just turn my attention to some of the companies that I've been working with, and some of the things that they've been doing. When I think about this, the things that have interested me personally, both in the companies I've worked with, the things I do in my shop, it's really about two things. The two things that I'm most interested in, the two attributes that I care about the most, are number one is things that haven't been done before. I just get a kick out of trying to do those things that haven't been done. And the second thing is learning the craftsmanship, the trade craft, the attention to detail required to do those things well. So when you look at the companies and you look at the things in my shop, those are the things that I have been most interested in, is really those two attributes. So here's a handful of the companies that I've been working with over the last couple of years. And let me just tell you a little bit about them. Mostly what they are the intersection of physical things controlled by smart hardware and software, microprocessors with smart software doing something. In the old world, we would have called those robots. But like as roboticists, the joke amongst roboticists is, a robot is what you call something before it does something useful. Once it does something useful, then it's a vacuum cleaner or a self-driving car or something else. And so I've mostly been working with companies that are really making robots. They just don't kind of look like these kinds of robots. And so let me tell you about the first company. This is an image of the Earth that in many ways changed our perspective about who we are and our place in the universe. And for those of us who were alive when this first image came down, this was mind-bending that this is what Earth looks like. And so I've been working with this company called Planet. And it's a bunch of NASA scientists who had been building these really expensive satellites. And they realized at one point that what is a satellite but really just an oversized, really expensive cell phone? And so they said to themselves, I bet we can build much cheaper satellites and put them up in orbit. So they left NASA, they started this little company, and they started building satellites that look like this. These satellites are about this big. Right now, they have 250 of these satellites in space, and they orbit the Earth, and they take pictures of the Earth every single day. And so they take a complete picture of the Earth every day. So while people had taken really high-resolution imagery before, this is the first time we've really added the time dimension to it so we can understand what changes on a daily basis. Here's one of their images. This is a picture of Alaska. This is the quality of imagery they take. But the most important thing about what these guys do is that they figured out how to detect what's changed in the world. And with that, you get kind of all of the implications, the understanding what's changed in the world. The building of refugee camps, the destruction of forest or coral reefs, the buildup. When the North Koreans launched a missile, they went back in time, they looked, they figured out the site by looking 2 or 3 days before. A whole bunch of cars and trucks show up at this remote site. It's there. You can see the vapor trail of the missile on the day that it launches. And then 2 days later, there's no more cars and trucks. And so it's kind of incredible, the implications of understanding what these things are possible for. Second company I've been working with is this one that's doing autonomous construction equipment. Bulldozers, backhoes, but done autonomously. The company's called Built Robotics. I got this slightly hokey video. Hope they don't hear me say that. But I'll show you because what they do is totally cool. So pretty wild. The third company I've been working with is a company called Zoox. And so while like doing that wind turbine farm is pretty easy, there's not much to get in the way. The third company is this company called Zoox that's building urban autonomous vehicles, urban taxis. Just think of an Uber, but without the driver. And the environment in which they're trying to do this is so much more complicated. And what's interesting about the company is that they decided in order to do this well, they needed to build a vehicle from scratch. So from the ground up, and they said, what would a car look like in a world in which we don't drive them? So the first thing is, well, you don't need a steering wheel, you don't need a gas pedal, you don't need a brake pedal, you don't need windshield wipers, you don't need mirrors. And you start going through this design problem, and it becomes an incredibly interesting one. And so what they ended up with is a vehicle that is basically 4 seats. It's like the back of a London taxi or maybe a stagecoach. 4 people sit in there as though you were in your living room. It's symmetrical. It has doors on both sides. It has fully articulating 4 wheels. So it's a completely different vehicle. So on one hand, they got to design something really interesting to solve a brand new problem. And the second part is they got to add this really complicated and interesting software to figure out how to navigate urban environments. So here's an image of what the computer sees. And when you think about these autonomous vehicles, what it really is a supercomputer on wheels. The amount of computing power that it takes to do this is unbelievable. It's, take 8 of the best CPUs you have and 8 of the best GPUs you have, and you stick it in a vehicle, and that's kind of the computing power that's there. And what you can see is an image that the sensors see, which are generally some combination of LiDAR, radar, and cameras, and then the processing and the classifying, and the colors indicate what the computer is actually seeing so that it can make decisions, it can classify the objects, and then plan the route. And here's a little video. And what you can see in this is you can see what the camera sees out of the various side view cameras. When you see the objects surrounded by the boxes, it means it has classified it, so all the pink ones are the pedestrians, and then down below is kind of a spatial representation of the same things that's showing up above. And so now you can see it in all kinds of tricky situations. You get used to looking at this thing as you look at the multiple images. But the amount of processing power that's going on is totally staggering in order to go through this. So what it's doing is running a neural network on these computers. It's figuring out what everything it sees in it. It gets an agreement between the multiple sensors, and then it decides on a path to go through. And it's been interesting because you've heard a lot of people talk about autonomous vehicles, and they talk about like the streetcar problem of what you'd hit and what you won't hit. My experience with these autonomous vehicles is completely different. The idea that somehow we will drive better than the computer is nuts. Given all our distractions, using our cell phones, talking to our friends, most of the time when we try to avoid something, at best what we do is we step on the brake hard. There is no doubt with a 360-degree view and all these sensors, these autonomous vehicles will step on the brake faster and more accurately than we will. And so I think a lot of people who have tried to predict the future, which often happens with new technology, have really been off on this. What it turns out is that the problem of not hitting things is actually the easiest problem. What's really the hard problem is the long tail of difficult situations and unpredictable behavior of humans. So I took a ride in one the other day, and we were just about to go down Lombard Street in San Francisco. But when you come up on the other side of Lombard Street, what you're often confronted with is about 40 or 50 people standing in the middle of the street with cameras on the top of Lombard Street. And now if the computer was really conservative, it would just sit there till about 2 o'clock in the morning until the street clears. So instead, what it has learned to do in a very subtle way is nudge forward, have the people move, nudge forward, have the people move. And when you look at that kind of sophistication in the kind of programming we're doing, you start to have a real appreciation. And so while right now, we're kind of in the down part of the hype cycle about autonomous vehicles, I promise you, if anyone takes a ride in one of these, you will realize that in the next 5 years, our roads are going to be filled with autonomous vehicles. So it's been really, really interesting. And one of the reasons that I think some of these companies are able to do what they're able, what I just showed, is this combination of really powerful hardware that's become cheap and available, and this incredible software. And it's really this combination that's really letting small companies and individuals do things that have never been done before. And when you think about it, this availability of hardware and software is kind of like the rewriting of the Industrial Revolution. The promise of the Industrial Revolution is if we made lots of things, we could make them at reasonable quality and reasonably cheap. And all of a sudden, we're able to do that, but do it with small quantities. We no longer need to make hundreds of thousands, and they don't all have to be black in order to get those economies of scale. And that's really what this promise of microprocessors and this new software is enabling us to do. So let's look back and think about this computer-aided design, which was the software that drives what's behind all of this. And, I've been involved with CAD for 35 years, something like that. Oh, God, it's hard to say that. It's been a long time. And I'm torn between two polar opposite opinions about have we accomplished much. We set out years ago to do a number of things, and we've gotten so far. And on certain days, when I'm mad at my computer and I can't get it to do what I want it to do, and my software is buggy and I'm sending notes to Kevin, I'm going, what the hell? We haven't made any. And other days, it's totally miraculous what we've actually accomplished. And and I was thinking back and going, what was the point of CAD and what were we needing to do? And as Kevin pointed out when he talked, the original idea was we were going to document our designs. We were going to make digital blueprints of the thing we wanted to build. But if you think back to the real purpose of that, there's kind of three things that we were able to do. The first one is kind of maintain the fidelity between our intent, between the design, and between the finished object. And we want to be able to keep that consistent throughout the entire thing. And if there's one thing I've learned through building and designing things all these years, it's that if you knew at the end of the if you knew at the beginning of the project what you know at the end, you would definitely do things differently. And what this software has enabled us to do is to get those insights earlier. We can build digital models of this and understand how it's going to function. We understand how we're going to make it. And the sooner we can do that, the better the end result will be. Eventually, and this is, so in many ways, nowadays where we can simulate, where we can run, digital simulations of our machine tools, we've accomplished a tremendous amount. On the other hand, when you think about what the possibility is, I think someday we should be able to sit there in our computers and basically turn on the thing we're going to build. We should be able to just flip the switch and experience it as if it was already built and understand everything about it. And in that way, we fall, pretty far short of what that goal is. Now, the second thing that I think is always important is to maintain consistency throughout the process. One of the things most of the tools have done well today, and Kevin showed it with his thing of 42-point solutions, is each of the tools works pretty well together. What really sucks for most of us users is the workflow between them. I will never use something that's no longer linked to the next step. That feels like, going back to the past. And so being able to maintain the associativity between all your tools so that, for example, when you change your design, my toolpath changes. That's what needs to happen, and I think there's no other way. And in that way, we've done a good job as well. And then the third one is making sure that teams of people can work well together. And I think that, the jury's still out. We're certainly further along. We can share files. We can share digital information. We can collaborate. But, we're not all of the way there. So, in some ways, I think when I look back and see the name computer-aided design, I go, it's a kind of humble name. The computer just aids you. It doesn't really do it. It's a lot of humility for the title of this kind of software. And as I think forward, it's probably fulfilled most of its promise. But as we do more, I think the next step is where we start to use the computer to actually help us really design things, to be able to talk to the computer in a way where we talk about the outcomes that we want, and what we get are the results. So we say, it needs to be this strong, it needs to be this stiff, it needs to be made of this material, it needs to be manufactured in this way. And as soon as we can do that, that's when we'll start getting beyond the humility of computer-aided design to really powerful tools that inform the process. And so this thing called generative design, I think, is incredibly important. And so let me show you, I've been doing some experiments in my shop. Many of these started a few years ago on generative design. So this is a chair that was modeled in Fusion. It was done as a generative design. We talked about, we specified to the computer a bunch of loads and a bunch of materials. And this is one of the chairs that came out as a result of that, and that we fabricated out of wood. There's a second one that was a similar design, and this is one that's made out of stainless steel. And as we talked about, the process of making some of these generative designs is hard. So one of the insights we had a number of years ago in making this thing was that I didn't want to make it out of plastic, but you look and you go, a MIG welder is really just a 3D printer if I could control it accurately enough. So what we did is, I've now built a number of these machines that have taken a store-bought wire-fed welder and turned it into a 3D printer to make generative design. And so here the next video will show you how I made this stainless steel chair. So I now have a small gantry system at home, just like an XYZ thing, and it has a MIG welder on it, and it can make all of these kinds of designs. The next machine I really want to make, because if you saw the picture of the stainless steel chair that was polished, is I really need a robot that knows how to sand and polish. I am getting way too old to sand and polish. And one of the bad things is I make these things and people see it and they say, oh, Carl, could you make me one of these? Could you make me another one? And I'd be happy to let my welder work all night long. I just don't want to have to sand and grind it because that's a hell of a lot of work. And then recently I just was trying out the software again, and this is a brand new design, slightly differently, of a new chair. And so when I get back, it's time to crank up the welder again and make another stainless steel version of it and get to work on that sanding, grinding robot. Second project I want to show you is my younger son came to me and said, oh, Dad, we got to build this canoe. And so he and I and a couple others have been working for a while on building this canoe. I'm glad a bunch of people in the room came up to me, and everyone's commenting on the canoe because it's been on Instagram. And so, but it's getting actually to the point where we're like, are you done with that canoe yet? Okay, he's off at college. We only work on it occasionally. It hasn't really taken a year and a half to build this canoe, but it's getting to the finishing point. Chris, who's in the audience, he and I, and we're all headed up to the Sierras this weekend to actually finally launch this canoe after a year and a half. But here's the canoe. And one of the things I want to say was I built a boat like this about 40 years ago. It was much harder to do back then. I didn't have the benefit of CAD. One of the huge advantages I had this time is I built a complete model of the canoe before I did it. I understood a bunch about it, just as we talked about, understood it. You understand where the mistakes are going to come, hopefully earlier in the process. And when I went to machine it, one of the very complicated pieces is the stem. All the planks come into the very front. There's an inner stem and then a laminated outer stem that goes on it. And so it's a painstaking thing to usually carve this thing precisely. This time I had a digital model, so I threw it on the router. And I precisely cut the stem. It took maybe 20 minutes to cut it. It was so easy. I made 4 of them just in case I need another canoe sometime. And this is where I go back to oh man, this stuff is so good. It works so well. This is exactly the promise that you want to have happen. And so, compared to the way I did this 40 years ago, using the router felt like cheating. But it was totally fun. So to top off the canoe, because as you know, I'm a big believer in generative design, we had to really go over the top. And the way you hang seats in a canoe is they hang from the rails, the gunnels, and they usually have a bolt or a rod or something. But we thought we'd take it one step further, and we would make some generatively designed brackets to hang our seats on. So there's the generatively designed bracket. Here's the setup on the 5-axis. So we put it on the 5-axis mill, and we ended up making these out of aluminum, and then we anodized them. And so there's the 5-axis generatively designed seat brackets for our canoe. And to put a cherry on top of this, kind of what good is having a CNC machine if you don't make some custom bronze hardware to finish it off and be able to tie up your canoe. So I am super excited not only to go canoeing, but to be done with a project that took a year and a half. I'm sure everyone in this room has one of those projects that's been sitting there for a little too long. The other thing I've been doing lately is I've been working on electric vehicles. This kind of started, my son had this idea to build an electric go-kart. We built an electric go-kart. When he went to college, I turned the electric go-kart into an autonomous electric go-kart. He came back from college and said, Dad, get all that shit off my go-kart. What sense does it make to have an autonomous go-kart? The whole point of a go-kart is to drive it. I try to go, well, you can drive it, then the computer will drive it, and we'll see who's fast. He was like, just get that shit off my go-kart. So I did, and I've taken on to bigger and better electric vehicles. This is my friend's dream that all of us in the shop have been helping out on. This is a Cobra. It's a kit Cobra, Shelby Cobra, that we've been making into an electric car. And it's been a totally fun project. My friend is someone I went to college with. No insult to too many people, but he's one of those mechanical engineers, who doesn't really know which side of the hammer to use. And he's very good at some of the other parts, but over the last 2 years, we've brought him into the shop. We taught him how to use Fusion. He runs the CNC machines and the water jets and everything. And with some of our help, we have this super kick-ass electric race car. We took it out the other day. We were going down the street in front. It doesn't have license yet or anything. And it was going about 20, and he stepped on the gas, and his rear wheels started spinning. The thing turned, it fishtailed sideways. It's about a G of force as you're going along. So it's a serious race car. So I saw his serious race car, and I decided that the vehicle that I was driving was really not what I wanted. So I went and I bought this 1950 Chevy truck, and I decided I would make my Chevy truck electric. So we yanked all the parts off the Chevy truck, put a brand new frame underneath it, and the idea is we're going to put 2 electric motors in line with the differential. And so exact same 2 motors that are in the Cobra, we were now going to put them in line in there. So one of the interesting projects, after having made those brackets for the canoe, we kind of realized that that 5-axis machining of that was a little bit of more of a pain in the ass than we really wanted to do for this. And so what we did is we did this interesting thing. Chris did all this work where he basically did generative design for the brackets. You can see them in yellow, and for connecting the 2 motors and then connecting it to the tubes of the chassis. So we did this generative design, but we did it in a way that it made mostly planar elements. And then with the planar elements, we kind of projected the silhouettes of them, and we then water jetted the parts and then just welded it. So we basically turned this complicated blob into a weldment and made the fabrication of it considerably simpler. And so here you can see the welding of this thing. And so we've been building generative parts. The motors are now back in the truck. We're waiting for the batteries, and hopefully I will get a truck on the road very soon, and it'll be much better than the vehicle I'm currently driving. So let me finish out with one thing. I made a promise to myself when I stopped being CEO. The mental model I had was like selling a house. And I didn't want to be the kind of homeowner who drove by the house they sold and I said, I can't believe those assholes painted it pink. Or, why did they cut down the maple tree? That was the best thing in the house. And so for 2 years, I've stuck to my promise. I haven't said a word, but it would really not be a return visit for my friends and colleagues in the Fusion team. I'm looking over there at you guys. It would really not be right, and they would really not even know who I am if I didn't come and tell them some things that I really think needed to be done to the product. So once I leave Portland in 2 days, I will go back to the mental model of I'm the homeowner and I don't care if you paint the house pink. But for right now, I had a couple things I needed to say, and since they gave me a stage, they're stuck listening to me. So here's the wish list. Okay, and it's just to make it better, Stephen. It's not a criticism. Okay, first thing, teamwork. There's 2 ways to phrase this. One is, I could tell you that it sucks working with Fusion as a team, or I could say nicely, please make it as good for working with teams as it is for individuals. I think many of us in this audience would all agree Fusion is an awesome thing for teams. There's a bunch for individuals when you come to working with other people, sharing tool libraries, sharing designs, working on the same design at the same time. It leaves a little bit to be desired. Give me some reinforcement, guys. They don't believe this. Okay, same way. You already have the cloud there. Let me share stuff. Half the stuff I have, you don't even let me share on it. So please just take advantage of it. Let me do the computation on the cloud. By the way, when the computation on the cloud's not working, let me kill the stuff on the cloud that's not working. And let me share all the information. All the infrastructure's there to do it. Like, we're this far away from some of the data management problems that could be so much better than anything that came before if you really took advantage. Third thing, manufacturing. Please finish CAM. 5-axis machining. There's a handful of things, some nesting. There's just a handful of things that if we could just finish that, I hate having to go and use other tools, go back to the old workflows that don't work, and you're so close. And so if you could just finish those things off. By the way, doing some of those projects like the electric vehicles, reverse engineering, handful of things, really important. I know you have other stuff in the thing, but just listen to us. There's people in this room who do this every day, and there's a handful of things we really need that would make our lives much easier, so do that. And then the very last thing is keep investing in generative design. This is just the very beginning. We're going to have 10 more years of development in generative, and while some of the things are already amazing and different and kind of spectacular, there's so much more to be done, and you have a great platform to do it on, so please just keep investing in it. Thank you very much.